so far we were discussing the laws of probability. So in the laws of the probability, we have a random experiment. As a consequence of that, we have a sample space. We consider a subset of the we consider a class of subsets of the sample space, which we call our event space or the events, and then we define a probability function on that. Now we consider various type of problems, for example calculating the probability of occurrence of a certain number in throwing of a die, probability of occurrence of a certain card in a drawing, probability of various kind of events. However, in most of the practical situations, we may not be interested in the full physical description of the sample space or the events. Rather, we may be interested in certain numerical characteristic of the event. Consider, suppose I have 10 instruments and they are operating for a certain amount of time. Now, after working for a certain amount of time, we may like to know that how many of them are actually working in a proper way and how many of them are not working properly. Now, if there are 10 instruments, it may happen that 7 of them are working properly and 3 of them are not working properly. At this stage, we may not be interested in knowing the position. Suppose we are saying 1 instrument, 2 instruments and so on, 10th instrument 1, 2 up to 10. We are not very particular whether instrument number 1 has failed or 2 has failed or 10 has failed. That means which 3 of them have failed may not be of interest. Rather, we are interested in the total number of the instruments which have failed and total number which are working. You look at say a game of basketball. Now, in a game of basketball, after the completion of the play, the score line will read something like say 95, 91. A team A may score 95 and team B may score 95. The outcome of the match is that team E has beaten the team B. To a particular observer, this particular phenomena or this basketball match has the final outcome that the team A won the game, or the final scores are 95 and 91. Whereas for a audience, they may be interested, they may be looking at which player scored how many baskets, what was the percentage of the possession of the team A over the team B over the ball, etc. So, similarly, if you consider a game of cricket, then suppose we are looking at a game of 2020, then team A scores say 168 runs for say loss of 5 wickets in 20 overs. Team B may score say 156 runs for the loss of say 4 wickets at the end of 20 overs. The outcome of the match is that the team A won over team B. Or if you look at the total scores, then these are the total scores. If you look at the total number of wickets, then these are the total number of wickets lost. We may not be interested in seeing that out of 20 overs there are 120 balls, at which ball how many runs were scored, how many balls were dot balls. These, although these are important data, but they may be useless for a certain person who is interested only in knowing what is the total number scored, total wickets taken, or a particular player scored how many runs or how many wickets he has taken. Therefore, for example, if we are looking at say weather, now the weather is a complex phenomena. So, if we look at say monsoon season, then during a full monsoon season the amount of rain varies day to day, from region to region, from time to time. That means in a particular day also a particular portion of the day may be dry, particular portion may be cloudy and particular portion may be rainy. Whereas for the weather scientist, individual phenomena may not be of interest. He may like to know that how much total rains are there in different zones of the country during the entire monsoon season. If we are looking at, say, crop of a certain variety and we look at the total yield, say wheat, then we may be interested in knowing that how much total crop of wheat was produced in India during 2008 to 2009. We may not be interested in knowing which plot of which farmer gave how much yield, or how many facilities were there because of which something happened. The total amount may be of interest to us. In effect, what I am trying to convey is that in order to effectively study a certain random phenomena or a certain random experiment, it is required to quantify the phenomena. That means, for every outcome we associate a number, a real number, and then we can study the probability distribution of that. That brings us to the concept of random variables. So, what is a random variable? Then roughly speaking, random variable, if we give a notation x, then it is a function from omega into r. That means, for every outcome we associate a real number. For example, runs scored by player, the baskets hit by a player in a basketball game, the yield of a certain crop, the amount of rainfall in a certain region, etc. So, all of this will correspond to certain event in the sample space, and we are associating certain real number there. So, in particular, any random variable is a real valued realization of a sample space. So, it is a function from the omega into r. However, to be more precise, because we have defined the probability function over a sigma field of subsets of omega. So, it is important that when we want to talk about the probabilities of associated with those numbers, then the inverse images of those subsets must be in the set B. So, this is called the condition of measurability, and a formal definition will then become, the formal definition of random variable is, so let omega b p be a probability space, a function x from omega into r is a real line, is called a random variable if it is measurable. So, to explain the condition of measurability, let C be a class of subsets of R, so that C is a sigma field. Then for any B belonging to C, X inverse B must belong to script B. This is the condition for measurability. An equivalent condition here is that we can state it in the form of a theorem. So, X defined on omega B is a random variable if and only if any one of the following conditions is satisfied. The set of omega such that x omega is less than or equal to lambda belongs to B for all lambda. the set of all those sample points such that x omega is strictly less than lambda belongs to B. The set of all those points such that x omega is greater than or equal to lambda belongs to B for all lambda belonging to R. The set of all those omegas such that x omega is strictly greater than lambda belongs to B. So, if any of these conditions is satisfied, then x is a measurable function and therefore, it is a random variable. As a corollary to this, the set of all those omegas such that x omega is equal to lambda, then this is also for all lambda belonging to R if x is a random variable. Similarly, if I consider the set of all those omegas such that if x is a random variable. So, these are some natural consequences. Let me just give a example here to show that how will you check the condition of measurability. Let us consider, say, tossing of a coin. Let us consider the random experiment of tossing of a coin. So, the sample space is here H t. We define the random variable x as the number of heads. So, naturally here x h is equal to 1 and x t is equal to 0. So, if we look at the set omega such that x omega is less than or equal to lambda, say. Now, if lambda is negative, then there is no point for which x omega is satisfying that condition less than or equal to lambda. That means, this is an empty set. If I take lambda is equal to 0, then x t is equal to 0. That means, there is a point here which is satisfying the condition that x omega is less than or equal to 0. You can observe that this condition remains true for lambda up to 1. That means, it is strictly less than 1, because the next value that random variable takes is actually equal to 1. So, when it eventually takes 1, then there are 2 points, that is h and t, which satisfy the condition that x omega is less than or equal to 1 or any point below above that. So, this becomes full omega for lambda greater than 1. So, if my sigma field here is consisting of, say, phi, h, t and omega, then you can see that this set is always belonging to B. Hence, this x is a random variable. Let us take another example, say tossing of, say, two dice. Here sample space is, say, 1 1 and so on up to 6 6, all the combinations of numbers I j for 1 less than or equal to I less than or equal to 6, 1 less than or equal to j less than or equal to 6, all the combination of natural numbers between this. So, if I define the random variable x as, say, the sum observed, and we want to write down the set omega, say x omega less than or equal to lambda. Now, if you look at this sum will vary from 2 to 12. So, if I have lambda to be less than 2, then this set is going to be phi. If I take lambda to be between 2 and say 3, then I have the point 1 1 here. If I have lambda between 3 and 4 greater than or equal to 3 but strictly less than 4, then we will have 1 1 1 2 2 1. If I have lambda greater than or equal to 4 but strictly less than 5, then this will become equal to 1 1 1 2 2 1 2 2 1 3 3 1. Like that, if I say lambda is greater than or equal to 12, then this will be full omega. So if I consider my sigma field here as power set of omega, then this will belong to B for all lambda, and therefore X is a random variable. The purpose of considering this measurability condition is that when I want to talk about the probabilities of these events in terms of random variable, then they should be well defined in the original sample space. Next, we talk about the probability distribution of a random variable. We have the following result. The random variable X defined on the probability space omega BP induces a probability space which we call R C Q by the correspondence QB is equal to probability of X inverse B, which is equal to probability of that the random variable takes values in the set B for all B belonging to C. Since it is a measurable function, X is a measurable function, therefore this set is belonging to script B here, and therefore this probability is well defined. We may write Q as Px inverse. Now immediately one should be interested to check whether it is a valid probability function or not. That means it is satisfying the three axioms of probability. We claim that this is true. Let us look at the first axiom. So QB, since it is equal to a probability in the original probability space, it is always greater than or equal to 0. If I consider Q of R, then it is equal to probability of the random variable taking values in R. Naturally it is probability of omega, and that is equal to 1. If we consider BIs as pairwise disjoint sequence of sets in C, then Q of union BI, I is equal to 1 to infinity, is equal to probability of X inverse union of BI by the definition of inverse, this is if BI's are disjoint, then X inverse BI's are disjoint, and therefore by applying the countable additivity axiom, and this is exactly equal to Q of BI. So all the three axioms are satisfied, and therefore R C Q is a probability space. So this Q is called the probability distribution of the random variable. So let us look at this example of head and tail. So here, if we say that the coin is fair, then you will have probability of H is equal to half and probability of tail is equal to half. Therefore, if I say probability of X is equal to 0, that is equal to half, and probability of X equal to 1 is half. So this is giving you the probability distribution of the random variable X. Since Q is a set function and here I am looking at the real numbers, so there is another function which we consider continuously, and it is called distribution function. So we define probability of X less than or equal to X as, say, f x of X. This is called cumulative distribution function of the random variable X. Basically, this is the probability of all the sample points such that X omega is less than or equal to X. So this is an abbreviation we will be writing down like this. This function is quite useful in talking about all types of probability statements of the random variable X. So first of all, this cumulative distribution function satisfies certain important properties. Properties of CDF. The first property is that if I consider limit of fx as x tends to minus infinity, that is 0. If we look at limit of fx as x tends to plus infinity, it is equal to 1. If x1 is less than x2, then f of x1 is less than or equal to f of x2. If I consider limit of fx plus h as h tends to 0, then it is equal to f of x. That means continuous from the right at every point. This is f is non-decreasing, right continuous at every point. To look at the proofs of this statement, we can consider the basic statements of the probability, basic properties of the probability. So let us see. To prove the property 1, let an be a sequence of let xn be a decreasing sequence such that limit of xn is equal to minus infinity. If I consider the sets an as the set of all those points such that x omega is less than or equal to xn, then limit of an is equal to phi as n tends to infinity, because if xn is a decreasing sequence, then an will be a decreasing sequence, and if I take limit of an as n tends to infinity, this will be the empty set. So now limit of probability of an is equal to probability of limit of an. So this is limit of probability of an is nothing but f of xn, and on the right hand side I will have probability of phi, that is equal to 0. So if I am considering xn tending to minus infinity, then this is equal to 0. So if along all the decreasing sequences to minus infinity, limit of fxn as xn tends to minus infinity is 0, then this implies that limit of fx as x tends to minus infinity must be 0. In a similar way, we can consider a sequence which is increasing to plus infinity, and then if we take the limit, take xn to be an increasing sequence such that limit of xn is equal to plus infinity. If we take this and apply the argument given in the previous one, then here we will have limit of an is equal to full space, and therefore limit of omega, limit of n will be omega, and here you will get equal to 1. To prove the third property, if I have x1 less than x2, then the set omega such that x omega less than or equal to x1 will be a subset of the set of all those omegas such that x omega is less than or equal to x2. So by monotonicity of the probability function, probability of this set will be less than or equal to probability of this set, which is equivalent to saying that f of x1 is less than or equal to f of x2. So the cumulative distribution function is a non-decreasing function. To prove the continuity from the right, let us consider a sequence. Let xn be a decreasing sequence with limit of xn is equal to say x as n tends to infinity. Now consider the set an as the set of all those points such that x omega is less than or equal to xn. Then these are measurable sets. An is a decreasing sequence, they belong to be ans are decreasing, and if I consider limit of an as n tends to infinity, then it is equal to, now you look at the definition here, I am considering this, however here I should put x less than this. So if I put this one, then since this is strictly x is strictly less than x omega, so if I take the limit here, this is going to be an empty set, that is intersection of an as n is equal to 1 to infinity is an empty set, because if I consider any point, x is not included in any of them, therefore it cannot be included in the intersection. So if I take limit probability of an is equal to probability of limit of an, then this implies that limit f of xn minus f of x as n tends to infinity is equal to 0, which means limit of f of xn n tending to infinity is fx. Now here xn was any sequence which was decreasing to x, that means a sequence from the right side of x. Now if it is true for any arbitrary decreasing sequence to x, then this implies that limit of fx plus h as h tends to 0 must be equal to f of x. This proves that the function f is continuous from right. This cumulative distribution function is quite an important function in order to define the distribution of a random variable. In fact, these 4 properties which we have given as properties of a CDF are also the characterizing properties of a CDF. That means, if there is a function which satisfies these 4 properties, then it will be CDF of certain random variable. So, I state this in the form of the following theorem. Given a probability function q on say R C, there exists a CDF f which satisfies q of minus infinity to x is equal to f of x for all x belonging to R. Conversely, given a function f satisfying the 4 properties, there exists a unique probability function q on R C such that q of minus infinity to x is equal to f of x. So, this shows that cumulative distribution function is it has a one-to-one correspondence with the probability function defined for a random variable, and it can be actually treated as equivalent to the probability distribution of the given random variable. So, let us consider certain examples here. Go back to the example of head and tail, and if we consider the fair coin example, here if we consider fx, then we are looking at the probability of x less than or equal to x. So, since the random variable takes the smallest value as 0, this probability is 0 for x less than 0. The probability becomes half when x becomes 0, and it remains so till x is strictly less than 1. It becomes 1 for x greater than or equal to 1. So, you can see here this function is continuous on the interval minus infinity to 0, open interval 0 to 1, and open interval 1 to infinity. If we look at the change points, that is at x equal to 0, the right hand limit at x equal to 0 is half, the value at x equal to 0 is half. So, it is continuous from right at 0. If we look at the right hand limit at 1, it is 1, the value at x equal to 1 is 1, therefore, it is continuous from right at 1. At all other points, the function is strictly continuous. the function is clearly non-decreasing. As x tends to minus infinity, fx is going to 0, and as x tends to plus infinity, it is going to 1. So all the conditions of the cumulative distribution function are satisfied here. Let us take one more example, that is of a die throwing problem where I defined the random variable to be the sum of the two dice. So in that example, if we make certain probability allotment, consider throwing of two die, two fair dice, and the random variable x was the sum. Let us look at the probability allotment here. So the probability allotment here will be probability of x is equal to 2. Now this is corresponding to the event that the outcome is 1 1. So let us look at the outcome 1 1. So there is only one outcome out of 36 outcomes. So if it's a fair coin, the probability of this will be 1 by 36. If we look at probability of x equal to 3, then there are two outcomes 1 2 and 2 1, which are corresponding to the sum being equal to 3. Therefore the probability that x equal to 3 will become 2 by 36. If we look at x equal to 4, then we will have favorable outcomes as 2 2, 1 3 and 3 1. There are three possible outcomes. So in this fashion we can write down probability x is equal to 5 as 4 by 36. The outcomes will be 1 4, 4 1, 2 3, 3 2. Probability x equal to 6 is equal to 5 by 36. Probability x equal to 7 will be equal to 6 by 36. The favorable outcomes will be 1 6 6 1, 2 5 5 1 and 3 4 4 3. Then probability x is equal to 8 will have favorable outcomes as 2 6 6 2, 3 5 5 3 and 4 4, that is 5 by 36. Probability x equal to 9 will have 4 favorable outcomes, so the probability will become 4 by 36. Probability x equal to 10 will be 3 by 36. Probability x equal to 11 will be 2 by 36, and probability x equal to 12 will be equal to 1 by 36, corresponding to only the outcome 6 6. Now if I want to write down the cumulative distribution function here, then we look at the set of the values that the random variable can take. It is taking values 2 3 4 5 6 7 8 9 10 11 and 12 with the positive probabilities, and all others are 0. So the starting point is x less than 2, then at equal to 2 you will have 1 by 36. It is equal to 3 by 36 for 3 less than or equal to x less than or equal to less than 4, and so on. It is equal to finally 1 for x greater than or equal to 12. So you can again see here that it is satisfying the properties of the CDF. As x tends to minus infinity it is 0, as x tends to plus infinity it is 1. It is a non-decreasing function and it is continuous from right. Let us check the continuity from the right at the endpoints of the intervals where the value of the function is changing. Suppose I look at x equal to 2, then the right hand limit at x equal to 2 is 1 by 36. The value at x equal to 2 is equal to 1 by 36. If I take the right hand limit as x tends to 3, the value is 3 by 36. The value at x equal to 3 is 3 by 36. So the properties of the cumulative distribution function are satisfied here. Let us take some problem. Say fx is equal to say 0 for x less than 0, it is equal to say x for 0 less than or equal to x less than half, it is equal to 1 if x is greater than or equal to half. Is it a CDF? If we check the condition that x tends to minus infinity, it is 0, that is satisfied. If I take x tends to plus infinity, the limit is 1. If I look at the non-decreasing nature of the function, that is satisfied. Let us check the continuity from the right. So, for the interval minus infinity to 0, for the open interval 0 to half, for the open interval half to 1, it is continuous. If I check at x equal to 0, the right hand limit at x equal to 0 is 0, the value at x equal to 0 is 0. So, it is continuous from right at 0. Let us take the value x equal to half. So, at the right hand limit at x equal to half is 1, and the limit as x tends to, and the value at x equal to half is 1, and the right hand limit at x equal to half is also 1. Therefore, the function is continuous from right. So, it is defining the CDF of a random variable. If we consider, say, f(x) is equal to 1 by pi tan inverse x. If we take x tending to minus infinity, this goes to minus pi by 2. So, this is not tending to 0. So, it is not a CDF. If I consider, say, f(x) is equal to, say, 1, 0 for x less than or equal to 1, it is equal to 1 minus 1 by x for x greater than 1. Once again check the conditions, condition 1, 2, 3, they are satisfied. The limit as x tends to 1, the right hand limit is 0, the value at x equal to 1 is 0, therefore, it is a CDF. This is a CDF. Suppose here I change to f(x) is equal to 0 for x less than 0, x for 0 less than or equal to x less than or equal to half, it is equal to 1 for x greater than half. Then you see here the condition of continuity from the right at the point x equal to half is violated, because as x tends to half from the right, the limit is 1, but the value at x equal to half is half. So, it is not continuous from right. So, this is not a CDF. Now, we consider classification of the random variables. From the examples that we have considered, for example, tossing of a coin, and the random variable was defined as the number of heads. So, it was taking values 0 and 1. If we consider the tossing of 2 dice and we took the random variable x to be the sum of faces appearing upwards, then it is taking values 2, 3 up to 12. However, there may be some other random variables. For example, I may be looking at the life of a bulb. Then the life of a bulb could be 1 hour, it could be 1 hour 5 minutes, it could be 56 seconds, etc. That means it is an interval. Therefore, the nature of the random variable is different from the ones which we considered just now. Similarly, suppose x denote the number of trials to needed for the first successful experiment with a certain drug to treat certain disease. Then the number of trials may be 1, 2, 3 and so on. That means the set of possible values of the random variable is countably infinite. So, based on this, we have the broad classification of the random variables, discrete and continuous random variables. So, a random variable x defined on a probability space omega b p is said to be if there exists a countable set E such that probability of x belonging to E is 1. That is, the range of x is at most countable. The points of E which have positive mass are called jump points. Or points of increase of the distribution of x, and the size of the jump is the probability of the random variable taking that point. So, the probability distribution of a discrete random variable is defined by a mass function. That means, the probability of random variable taking a particular value, say xi, where xi will belong to a countable set E. So, it will satisfy the following properties. We call it a probability mass function. Of a discrete random variable. So, it is defined by a mass function p x xi. It will satisfy the properties. So, this is actually probability of x equal to xi for xi belonging to the countable set E. So, we must have p xi strictly positive and sigma probability of xi is equal to 1 for xi belonging to. So, if we look at the examples discussed earlier, the tossing of a coin, the throwing of a die, etc., then the probability distribution is quite clear. For example, let us look at this one, the die throwing problem. So, here it is exactly p x, you can write it in the terms 4 3. So, we can write p x 2 is equal to 1 by 36, this is p x 3, this is p x 7, etc. It is clearly satisfying the properties that p x xi is greater than 0 for xi belonging to the set here. Here what is the set E? The set E is here 2, 3 up to 12. Now, from here you can establish a relationship between the cumulative distribution function and the probability mass function. The cumulative distribution function can be expressed as f(x) is the sum of all those values of the probability mass function for which xi is less than or equal to x. Conversely, p x xi can be written as probability of x less than or equal to xi minus probability of x less than or equal to xi minus 1. So, this will become f of xi minus f of xi minus 1. Let us take one example. A computer store contains 10 computers, of which say 3 are defective. A customer buys 2 at random. Let X denote the number of defectives in the purchase. Then the possible values of X can be 0, 1, 2. So what is Px0? Now this event corresponds to that out of 7 good he has chosen 2 divided by 10 C2. So this is equal to so it is 7 into 6 by 2 divided by 10 into 9 by 2, which is equal to if I consider probability x equal to 1, then it is equal to 7 C1 3 C1 divided by 10 C2. If we consider Px2, that means both he has purchased as defective, then it is equal to 3 C2 divided by 10 C2. So all of these values can be calculated. 3 by 45, that is equal to 1 by 15. This is equal to 21 by 45, and that is equal to 3 by 45. Now here if I want to write down the probability cumulative distribution function, it is equal to 0 for x less than 0, it is equal to 3 by 45 for 0 less than or equal to x less than 1, it is equal to 22 by 45, 24 by 45 for 1 less than or equal to x less than 2, and it is equal to 1 for x greater than or equal to 3. Now you look at the jump points of this distribution. So here at x equal to 0 there is a jump of size 3 by 45, which is equal to the probability of random variable x taking value 0. I think we have made some mistake here. It is not equal to this. It is 7 into 6 by 2, that is equal to 21, and divided by 45. So 21 by 45. 21 by 45. So this is equal to 42 by 45 and 1. So the probability of x equal to 0 and x equal to 1 is 21 by 45, and the probability of x equal to 2 is equal to 3 by 45, that is 1 by 15, which is equal to the size of the jump at the points 1, 2 and 0, 1 and 2 respectively. Thank you.